Hello everyone. Today we'll be presenting our work on designing an interactive graphical user face for binary multiplier. Today let's discuss binary multiplier circuits. A binary multiplier circuit is a crucial digital circuit designed to perform multiplication on binary numbers, which are foundational for modern digital systems. These circuits form the core arithmetic logical units, or ALU, inside modern processors. Essentially, without binary multipliers, computers wouldn't be able to perform many complex mathematical operations that enable everything from simple calculations to processing huge amount of data at incredible speeds. If you look at the diagram and keywords here, the two main strengths are highlighted: digital logic and fast processing. Digital logic refers to the use of logical gates, especially AND gates and adders, to manipulate binary values. Fast processing means these data can compute results in parallel, significantly speeding up calculations. In summary, binary multiplier circuits are foundational for digital computational, enabling both high-speed and accurate mathematical operations within processors. Let's break down the core components of binary multiplication circuits. There are essentially three building blocks: AND gates, binary adders, and shift logic. First, AND gates generate what are called partial products. They do this by carrying bitwise AND operations between each bit of numbers being multiplied. Every AND gate is responsible for producing one bit of a partial product. Second, binary adders sum up those shifted partial products. These adders come in two variations: half adders and full adders, both of which are essential for handling carry bits in binary addition. Their main job is to ensure all the partial results are added together correctly, taking into account any workflow or carry that might result. Finally, shift logic is used to align the partial products properly. When multiplying, the results for each successive bit of the multiplier must be shifted over the left, and the alignment is controlled by shift logic. It ensures all pieces of the partial products are added to the right column, mimicking how multiplication is done by hand but in binary. Together, these components, AND gates, binary adders, and shift logic, work in harmony to perform efficient binary multiplication, which is central to the operations of a digital processor. Now, I'll pass on to Abhilash.
Okay. Now I'm going to explain a step-by-step process of how binary multiplication works. Binary multiplication works in a way that is very similar to decimal multiplication, but instead of digits from 0 to 9, binary numbers have only two digits, 0 and 1. The key rules of binary multiplication are very simple. 1 is to 1 is equals to 1, 1 is to 0 is 0, 0 into 1 is 0, and 0 into 0 is 0. So the multiplication itself is done just using the AND logic. To perform binary multiplication, we multiply each bit of one number with every bit of the other number. This creates what are called partial products. These partial products are then shifted to the left depending on the position of the bit we used. Finally, we add all the shifted partial products together to get the final result. And this is exactly like how we multiply decimal numbers, where we write rows of numbers and add them. Only here, everything is done in binary. Inside the circuit, we don't do these operations manually. Instead, the circuit uses AND gates to generate partial products automatically. Each bit of the multiplicand is added with each bit of the multiplier. Then, to add the partial products, the circuit uses binary adders, mainly half adders and full adders. Whenever a bit is in a higher position, the circuit simply shifts that partial product to the left, which is like adding zeros in binary. Finally, after all partial products are added, the result forms the final binary product. So how does the GUI represent this? The GUI makes this entire process easy to understand. It allows us to enter two binary numbers. Behind the scenes, the GUI performs the same steps. It generates the partial products, it shifts them according to position, and adds them using digital adders. But most importantly, the GUI shows these steps visually so we can see how multiplication is happening bit by bit and then finally displays the binary product. The user input features include real-time conversion between binary decimal and hexadecimal and preset examples for quick demonstration and learning, while the visualization capabilities include step-by-step animation showing the partial product generation. It highlights active logic gates during the operation phases and displays carry propagation through adder chains in real time. Now I would like to pass it on to Gitika.
Thank you, Abhilash. So, understanding binary multiplication circuit is the key to understanding how computers think and compute at the hardware level. It bridges the gap between theoretical digital design and real world computational hardware. So this circuit is a 3 into 3 binary multiplier. The diagram represents a binary multiplier that multiplies two 3-bit numbers, one multiplicand, that is B2, B1 and B0, and one multiplier, that is A2, A1 and A0. The output is a 6-bit binary product. It demonstrates how binary multiplication can be built using logic gates and adders instead of manual arithmetic. AND gates generate partial products like AI into BJ. Each bit of the multiplier, that is A, is passed through AND gate with every bit of the multiplicand, that is the B gate. These AND gates produce partial products such as A0 B0 or A0 B1, A0 B2, A1 B0, etc. This step is similar to multiplying each digit in normal decimal multiplication. In the diagram, three rows of AND gates correspond to A1, A0, and A2. Partial products are shifted according to multiplier bits. In binary multiplication, each successive row for A1, A2 is shifted left by 1 and 2 positions respectively. The shift accounts for the binary place value, just like adding zeros in decimal. The diagram shows this by how each row and outputs enters the adder with shifted connections. 3-bit adders sum the shifted partial products. The first 3 adder adds the first 2 partial products, that is A0 into B, and shifted A1 into B. The second 3-bit adder adds the result to the third shifted partial product, A2 into B. These adders combine all partial products to form the final sum and carry outputs. Final 6-bit output, that is P5 minus P0, gives the binary product. After all additions, the circuit produces the final 6-bit binary result, that is P0 into P1, P2, P3, P4, and P5. P0 comes directly from first AND gate output, that is A0, B0. Higher bits like P1 to P5 are obtained from the adder sums and carries. Together, these 3 bits represent the complete product of the two 3-bit inputs. Now let's understand about the real life examples. This is the 3-bit adder, half adder and full adder, as you can see. Yes. Binary multipliers are crucial in nearby all digital systems that require arithmetic operations. Let's elaborate on each. Microprocessors. So
Binary multipliers are integral to CPUs and ALUs, that is logic units. They perform fast arithmetic operations such as addition, subtraction, and multiplication. These enable high-speed computation in essential for running software applications like gaming and data processing. Second is graphics processing, GPUs, are multipliers extensively for rendering images, performing 3D transformations, lightning calculations, and pixel level operation. This allows real-time graphics rendering in games, animation, and video editing. Then signal processing. In digital signal processors, also known as DSPs, binary multipliers are used for mathematical operations such as filtering, convolution, and fast Fourier transforms. These are essential for processing audio, video, and communication signals efficiently. Then, cryptography. Binary multipliers handle large integer arithmetic used in encryption algorithms like RSA and ECC. They help secure data transmission and perform fast cryptic computations for authentication and privacy. Then AI accelerators. Artificial intelligence hardwares like tensor processing units relies on matrix multiplication during neural network inference. These operations use large arrays of multipliers to perform computations in parallel, improving AI speed and efficiency. And lastly, mobile devices. Mobile chips, system on chips, include power efficient multipliers to perform multimedia operations like image processing and computational photography. They ensure better performing while minimizing battery usage. Now, to conclude, the binary multiplier circuit showcases the combination of digital logic simplicity with the power of parallel computation. It serves both educational and practical purposes. So let's talk about educational values. Help students understand digital logic, Boolean algebra, and computer arithmetic. Through GUI simulations, learners can visualize complex processes like bitwise addition and shifting, making learning interactive and engaging. Now, the practical impact. This has practical impact too. Binary multipliers are the foundation of all computing systems, from embedded devices to supercomputers. As technology advances, optimization techniques continue to make these circuits faster and more efficient. Thank you.